Thank you very much for having me here. I'm Saikat Guha. I'm a professor at the University of Maryland, College Park. I was at University of Arizona before I moved here just 3 months back. So I'm just going to give you a very high-level introduction to a center called the Center for Quantum Networks. It's funded by the National Science Foundation. We are in our 4th year. It's a full-stack quantum networking project involving many academic partners, industry partners, and government stakeholders across the US. So this project and the whole ecosystem of associated projects, several that we collaborate with many government labs, including Oak Ridge National Laboratories, we heard from Nick a little bit ago. It has to do with this really long-term vision of a quantum connected world where you have connectivities between quantum gadgets, quantum processors, sensors, computers, handheld devices, data centers across small scales and across long scales that can carry qubits from one point to another reliably and at high speeds. The quantum internet is the vision that adds this new service of quantum communications to the existing internet as an additional service. The quantum internet does not make the classical internet faster. It adds a new service called quantum communications that helps you do things that the classical internet cannot. One of the biggest challenges of building the quantum internet is that sending quantum information from one point to another accrues a fundamentally different scaling of the way the rate of communication goes with the distance of transmission. And traditional optical amplifiers, where they're used in classical internet, they don't work. And they kill the quantum information even before they would arrive. And in order for you to build a scalable quantum internet, you have to build this thing called the quantum repeater. A repeater is a special purpose quantum processor. It's a quantum computer, you can think of sorts, that has quantum memories, a good number of them, an interface that can have those memories load on offload qubits into the photonic domain, because photons really are the only form of qubit that can fly long distances. And you also need some amount of quantum logic on those memories to do things like error correction. And you want classical communications and classical computing. So that repeater, building that, is a big part of this project's goals, involving people all the way from expertise in the chemistry and the physics of novel quantum materials to people who are understanding the novel design of interfaces of those spin qubits and the photonic qubits, developing error correction codes that are specifically designed for repeaters, and up a layer to people who are experts in computer networking, who are working on figuring out how to design architectures, routing protocols, scheduling algorithms, and so on. So it involves people all the way from chemistry, physics, photonics engineers, electrical engineers, mathematicians, and computer networking theorists. So before I tell you a little bit more about the center, the first question is, why care? Like, what does quantum connectivity at different length scales buy us? And as I said, the first misnomer about quantum internet is that it will not buy us more speed of classical data communications. In fact, I would go as far as to say that adding this new service on the internet is actually going to draw on the resources on the classical internet, because quantum communication requires classical communications to work. So one of the biggest challenges is to design the protocol stack for the quantum internet that is the most cognizant in terms of its usage of classical computing and communication resources. There's a whole variety of things that this quantum connectivity at short and long ranges can buy us. These are just few examples. We all have heard of different forms of network security protocols that use quantum communication as a service, QKD being the big example. But there's also a huge set of topics. One DARPA program that I'm part of called Quantum Augmented Networks, funded by the I2O office. Alison O'Brien is the program manager. It's looking at a variety of network security primitives that can be boosted by augmenting the physical layer of the quantum network with non-classical light sources like single photons, squeeze states of light, entangled photon sources, trying to catch an intruder quicker, try to catch data exfiltration from your network enclave, try to find out if there has been a route injection attack and things like that. And then quantum communications across a really, really long distance at the global scale, for example, which could connect, for example, a bunch of optical telescopes looking at a correlated event. It can immensely benefit from having entanglement pre-shared between them compared to them just collaborating classically. So long baseline astronomy using quantum entanglement is one of those really long distance visions, but if it does come to fruition, it holds a huge promise. This is, again, another topic that we have heard about in other contexts in this conference, blind quantum computing. And a whole suite of things that have come out of the original papers that Andrew wrote in blind quantum computing. Once quantum computers get put on the cloud, they're already being put on the cloud by IBM and many other companies. If you want provably private access to those quantum computers, you want to be able to run your algorithm on that, but you don't want that service provider to know what you're doing with it. There's a suite of algorithms that fall under this class that can only be supported if you had a quantum connection to the cloud. If you only had a classical way to communicate with the computers on the cloud, you don't get this sort of a proven private access. Pre-shared entanglement between two parties. If you are photon starved in terms of your communications, your transmitter, maybe because you're trying to save on battery, or perhaps in a tactical environment, you are trying to remain undetected. You are trying to do covert communications. Then pre-shared entanglement can give you a significant boost over not using entanglement. You're transmitting using long wavelength, for example, infrared light at a very low transmitter brightness. Very niche, but interesting example of entanglement over a network. Sensors is a huge topic that I know that many people here and many industry stakeholders, government program managers, and academics are interested. This is only a partial list. The idea behind sensors using entanglement is that when there's a bunch of sensors trying to do a sensor data aggregation task, if they're looking at some correlated set of signatures and trying to discern some function of what they are seeing. For example, there's a bunch of sensors, they're trying to detect the gradient of the magnetic field, or there's a bunch of sensors that are trying to work together on doing an astronomical event observation, small scales, large scales. Entanglement between them as a resource can help them do far better in terms of the resolution performance. It has applications in, say, RF photonic sensors where the entanglement lives within the sensor array. Applications in atomic force microscopy where the entanglement is between the set of co-propagating spatial modes of a scanning probe microscopy probe that is being used for sensing some optomechanical system. Nitrogen vacancy-based magnetometry is a huge topic of interest to the field right now. If you entangle these atomic systems that are sensing magnetic field, you can become exquisitely powerful sensors of magnetic fields, and so on. And finally, there's another very interesting application of entanglement completely within the receiver for applications to designing receivers for deep space laser communications, right now being funded by NASA in our group. So there's a whole bunch of topics that our group is interested in. We work with many collaborators across the ecosystem. But entanglement across short scales, medium scales, long scales, it has many applications that are known and many that will that are probably not known right now. This is how CQN as a center is organized. We have 4 research thrusts. Thrust 1 is an architecture thrust that is designing the overall architecture of the network. Thrust 2 is the subsystem thrust. This is where our quantum repeaters, our spin photon interfaces, our error correction modules, they all bubble up. That gets put together into the final system. And Thrust 3 is a collection of a variety of devices and fundamentals. We have 3 test beds. The major test bed is situated at the University of Arizona, Tucson. So I founded the center 4 years back. Right now, the center is kept headquartered at the University of Arizona. UMD is a core partner of the center. Now, my colleague Matt Eichenfield at University of Arizona and I are co-directors. U of A has a network testbed that involves 6 nodes across the campus with 10 building sites, equipped with 2 forms of quantum memories, silicon vacancies in diamond and tin vacancies in diamond. And the experiments involve entangling these hybrid forms of quantum memories using quantum versions of our add and drop multiplexer. And then ultimately, we are going to entangle these memories with trapped ion registers built at University of Maryland that bring in error correction ability into those networks. If you're interested in learning more about the details of the various research thrusts, starting all the way from memory development to the network layer work, I'm happy to talk to you later in this conference. There's a very interesting 4th thrust that is part of our ERC that is exclusively studying societal impacts of the quantum internet. And this research thrust is comprised of researchers with backgrounds in social behavioral sciences, economics, law, policy, and so forth. For the experts in the audience, this is just one sneak peek at the setup that is being built at the University of Arizona testbed. We are connecting a silicon vacancy color center node with a tin vacancy color center node with a master laser that is distributed across the network that serves as a local reference for second harmonic generation and some frequency generation for making the memories compatible in terms of the resonant wavelength that the photons emit at. And this architecture, you can bring in different forms of memories as the technology evolves. There's a lot of interesting work on tuning the emissions, getting them to be fabricated on a photonic integrated circuit in a scalable fashion, designing the interfaces with photons, and then building the cryo-electronic processing, the RF electronics, and everything that goes with it. We are building a full-scale simulator for the quantum network, led by Stefan Krastanov at UMass Amherst. We also built, we have an education workforce development program as part of which a student of mine, Ashlesha Patil, she built a game of Tangram. You must have played some form of game of Tetris, but if you get better at playing her version of the game, you will unknowingly also get better at mapping a quantum circuit more resource effectively into the measurement-based model of quantum computing, which is how error correction and distillation gets done for quantum repeaters. If there are industry members in the audience, feel free to reach out to me if you want to talk to me about how you might become a part of the center. We have roughly 25 member companies that work with us at different capacities. The diamond members are the top tier members that actually do research working with our center. So with this, I'll stop here and take any questions if there is any time. Thank you very much.